Hello everyone, and welcome to AISC's Night School. This is Night School 6, Bracing Connections and Related Topics, presented by William A. Thornton. Today is September 22nd, 2014, and this is Session 1 on Basic Principles. My name is Brent Liu. I am with AISC, and I will be moderating today's presentation. I'd like to introduce this evening's speaker, William A. Thornton, PE and PhD. Dr. Thornton is a corporate consultant to Surveys Corporation of Roswell, Georgia. He is the winner of the AISC 1995 T.R. Higgins Lectureship Award, and in 2003 he was awarded the AISC Lifetime Achievement Award. He has served as an invited lecturer numerous times at AISC and at various state Structural Engineering Association seminars on his specialty, connection design. He is the author or co-author of many published papers on connection design, as well as other structural areas. He's a member of ASCE, AWS, and RCSC, and he was the chairman of the AISC Committee on Manuals for 20-plus years. His most recent award was given to him in 2013 when he was elected into the National Academy of Engineering. Very pleased to have Dr. Thornton here tonight. Bill, welcome. And I'm going to hand things over to you.
Thank you, Brent, and welcome everybody. Good evening, good afternoon, depending on where you're at. This course has got to do with bracing connections and related topics. There's the first slide. The next one gives you a course outline. This is for each of the 8 sessions. This one is session 1, will be basic principles, and then the others are listed here: the uniform force method, bracing connection details, and prying action. Vertical bracing connections corner part 1, that's basically going to be non-seismic, and then vertical bracing connections, session 5, again corner, seismic connections. And then 6 and 7 will be chevron gussets, the first one for wind and low seismic, the usual situation, and then chevron gussets for high seismic, including mechanism analysis. And then 8, the last session, will be additional connection topics, things like development of fills, splices. Perhaps we'll get into base plates, gussets coming down to base plates. So, starting for tonight, basic principles. And here's the outline for tonight's session, or this afternoon's session as the case may be. Introduction, limit states, code of standard practice, principles of structural mechanics, the lower bound theorem, and some comparison of various connection design methods. This slide shows a typical bracing connection, which hopefully by the end of this session you'll be able to design something like this. It's pretty complicated stuff, but it all is based upon simple initial or first principles. These just show kind of simple corner connections and chevron connections that I just mentioned. We'll be talking about these in some of the various sessions. We may get into, in session 8, gussets coming down to base plates. And then, as one of my lead-in slides, wasn't exactly this, but this is kind of a tree situation where you've got 4 braces coming into one column, and the beam stubs are there, and it's erected as it's called a tree system. I haven't used that in a while, but that was a common procedure not too many years ago. So that's just sort of an introduction. We're interested in bracing connections. Bracing connections are something that I've been interested in for, 30-odd years or so. And I guess you might say it's my specialty. The next part of this is limit states, the spec, the specification, the manual, and other documents. And the next set of slides has got kind of going through some of these just to point out where things are. Connection limit states. In this section, we will briefly discuss common connection limit states and where they can be found in the AISC specification. The organization of the steel construction manual as it relates to connection design will be reviewed. Finally, since not everything can be contained in these two documents, maybe it could be, but it isn't, other useful resources are also presented. So, limit states. In the specification, limit states governing connection design are found in these chapters of the specification. B, local buckling, and also there's discussion in there of what a simple connection is. Chapter D, we get into net tension and shear lag. In Chapter D, there's other things in Chapter D, but that's what we'll be covering here. Chapter J is really the principal connection, chapter on connections in the specification. Chapter K also has a lot of connections, but it's for HSS, and we will not be covering those specifically in this seminar, this webinar. Appendix 3 for fatigue has got lots and lots of details. Likewise, we will not be covering those in this particular seminar. And then there's the AISC seismic documents. We will be getting into those. 310 particularly, AISC, ANSI AISC, what? 341.10. Sorry, I had the wrong number there. So let's start in Chapter D, area determination. What are we doing there? There's net area. There's a table D 3.1 that's got a lot of different sections shown in it, effective net area. There's a couple of things that are kind of grayed out here that we will not be talking about in Chapter D, which are built-up members and pin-connected members. Chapter J, the most important chapter probably in the specification for connection design, is made up of lots of sections, but I've got some listed here. General provisions. Then we've got wells, J2, bolts and threaded parts, J3, J4, affected elements of members, like the members that are affected by shear, and axial, and flexure, and buckling. Fillers, I hope to get into that in the 8th session. There's a lot of really good stuff in the 14th edition, the latest specification on the development of fillers that came from work of Jerry Hajar at the University of Illinois, and that's in the new spec. It is not in the 13th edition spec, but the 14th. We'll talk about in the context of bracing connections, flanges, and webs with concentrated forces. That will come in some of the examples that will work. Then the seismic documents. Seismic connections are generally required when using the seismic load reduction factor, R greater than 3. Information regarding seismic connections can be found in the seismic provisions. ANSI AISC 341.10 is the general provisions, and then there's the ANSI AISC 358.10 for pre-qualified moment connections for special and intermediate moment frames. We will not be getting into those. I believe those were covered to some extent in the first night school on connections. Weld rupture. We'll be talking about that. Section J 2.4. It's interesting to note that relative to welds, the only limit state on the base metal now in Section J 2.4 has to do with rupture. That's in the 14th. If you went back to the specification in the 13th edition, it had rupture and yield. That's no longer true. So that's a change. It's kind of a subtle one, but you should take a look at that section and see what I mean. For bolts, we'll be looking at bolt shear, bolt tension, slip critical connections, then interaction, shear and tension for bearing connections, and interaction, combined shear and tension for slip critical connections. And these are sections J 3.7 and 3.9 respectively. Continuing, bolt bearing. I guess this is all kind of what I call boilerplate, but it's just trying to give you an overview of where to find all this stuff. We will be doing a number of problems where we actually do these things. I don't know that I will always be telling you exactly which section it's in, But the lead-in here tells you where it is. Bolt bearing. There's really two requirements in bearing. One is bearing, and the other one, which is still in the bearing section, J310, is called bolt tear-out. I prefer to call them different limit states because they really are, but the specification still, even the 14th edition specification, calls both of these bearing. Block shear, J3.4. Flange local bending is grayed out here. We won't be discussing that. I don't believe in any of these problems, but web local yielding we will, and web crippling we will. And web side sway and web compression buckling and web panel zone, which really is for moment connections, we will not be covering any of those. Continuing, for connecting elements, there's yielding, tension, and shear. And these specification sections are given here. For tension, J4.1, for shear, J4.2, for fracture, net tension fracture. Or I think the specification prefers the word rupture, but I really like fracture. That's in J4.1 again, and net shear, fracture, J4.2, and buckling. J4.4 is really buckling of elements, of connecting elements. And that's the place where you find that if the slenderness ratio is 25 or less, essentially yield controls and buckling can be ignored. Prying action. These are now things that are beyond the specification. Prying action is not in the specification per se. It's mentioned that you need to consider it, but it doesn't tell you how to do it. Prying action has been really in the specification since the 7th edition. The 6th edition, way back in the 60s, did not have anything on prying action, if I recall. And what's in the 14th edition manual is essentially the same thing that's been in there since the 8th edition, more or less, and definitely the 9th AISC manual, and every other manual since about 1984. Yield line analysis comes into a great extent in many of these connections, and there's a couple of papers referenced here. There's Anand and Bert's EJ, second quarter 1981 is a good paper to look at, and there's a chapter that I wrote in a book by Akbar Tamboli called Handbook of Connection Design. The details, I think, is in the 2nd edition, I think about 2010. The Whitmore section, part 9 of the manual. It's mentioned there, but there's a good paper that by myself and Carlo Lini in the Modern Steel Construction of a couple of years ago that you might want to take a look at, that kind of explains, I think, all you need to know about the Whitmore section. Continuing, for the manual, part 7 is really all you need to know about design for bolts. Eccentrically loaded bolts, the theory that's used, there's a discussion in there of the inelastic and the elastic methods. Part 8's got to do with welds. Everything you need to know, I think, pretty much about the design of welds, strain compatibility and things of that sort. Part 9, the design of connection elements, that's where prying action is, spelled out in pretty good detail. Rotational ductility, which is some requirements to ensure that we have connections that satisfy the specification section B 3.6A, I believe it is, where these rotational connections or simple connections are not supposed to be able to develop very much moment. And there's some tests in this particular part of Part 9 that you can use to assess that. And also this part does copes, various copes, top copes, bottom copes, double copes. And it's got a whole set of tables that allow you to come up with the properties of the sections of, say, coped beams where the top flange is coped, so you have a T-section. There's properties in there to make that design simple. Part 10 has to do with design of simple shear connections, basically those that satisfy specification D 3.6A, so they don't develop a lot of moment. There's discussion in here of constructability. There's shear connection tables. There's extended gauges. There's skewed connections. All kinds of really complex connections are discussed in this part of the book. Part 11, design of flexible moment connections. I don't think there's really a lot in the manual on that. That's kind of the old wind connection, the old Type 2 construction, which is not very much used anymore. I don't even know if it's allowed anymore. I don't think we even talk about Type 2 anymore, but there's still discussion of flexible moment connections. These are connections that are supposed to be able to take wind, and I really haven't done anything with them recently, but there's a bunch of papers that Bob Disquay wrote some years ago that kind of showed how to do this. Part 12 is basically moment connections, fully restrained moment connections, and also moment splices. And Part 13, which is sort of the meat of this particular night school, design of bracing connections and truss connections. The uniform force method, there are 3 variations given in there. There's the full-blown uniform force method, and then special cases 1, 2, and 3 that we will discuss not today, not tonight, or this afternoon, but the next time, the second seminar. Part 14, beam bearing plates, column base plates. We won't be talking much about this. And then hanger connections, Part 15, bracket plates, crane rail connections, just a lot of potpourri of things that kind of stuck it all together in this place. In Part 15, there's a table that gives you, that allows you to get plastic or plastic section moduli for net sections that satisfy certain requirements. Just makes it easier than having to calculate it every time. Chapter M of the specification doesn't really have a lot to do with connections, but we put this in here because there are some tolerances on, for instance, column splices. There's information on there on column splices. How bad can the mating surfaces be before you need to shim them? So continuing on, that's the AISC specification and manual. And then other sources of information, the Research Council on Structural Connections, RCSC. This is the specification. These people put out the specification for structural joints using high-strength bolts. This is the bolt spec listed there in parentheses. It used to be called the specification for A325 and A490 bolts, but the name was changed for the latest edition of it because of the twist-off bolts that have different numbers, and so this one now covers them all. A325 and its twist-off variation, and A490 and its twist-off variation. Then the guide for design criteria for bolted and riveted joints. This basically was the book that was produced at Lehigh University originally in 1974 by Fisher, John Fisher, and Struick. And it was reissued again in 1987 with Geoff Kulak as the leading author. It's a good book to have if you want to know where some of these things came from, the design criteria for bolts. It's a free download from www.boltcouncil.org. There's also some other documents on that website. The education section is listed here that might have some useful information. Continuing, other sources, AWS. The Bible for structural welding is the first one here, D1.1. It's been around for a long time. You really need to have a copy of this in your library to make sure that you're getting it right. AWS has some, AISC, the AISC manual has got some of this in there, pre-qualified joints. A lot of the stuff that you really need is in the manual, but AWS D1.1 is where it comes from. Then this 1.8 is a relatively new welding guide for seismic welding that's got things like what's the word? I can't remember it. The fracture critical weld, things of that sort. That you need to have that if you're doing seismic design. Then there are the AISC design guides. There's I think we're up to number 29 now. There's all kinds of design guides that for various kinds of problems like base plate, extended end plate, partially restrained composite connections, modification of existing steel moment frame connections for seismic resistance, wide flange column stiffening. The last one there is by Charlie Carter. That's just a listing of a few of them. Here's another one, flush and extended multiple row end plate connections. Probably went through that in some detail in the first webinar or night school on connections. Then the last two here, high strength bolts, a primer for structural engineers, DG17. That one's by Job Kulak. And the last one, welded connections, a primer for engineers, DG21. That's by Dwayne Miller. These two are not specific to any particular kind of application, but rather just good information on bolts, DG17, and wells, DG21. And I would recommend, if you don't get any of these other design guides, that you at least have those two and maybe read them. I mean, they're pretty easy to read, and they're interesting. It's interesting stuff to know. These design guides can be downloaded from AWS, from AISC Freedom members. Okay, what else do we have left? We've got Modern Steel Construction, the magazine, monthly, that comes out every month. It's got lots of information in it. It has a section that's called Steel Interchange, which has questions that sometimes are answered by the Steel Solutions Center, the third bullet item here. You can call AISC's or go to AISC's website and look at frequently asked questions, and maybe the answer to your question is there. And OSHA. You need to know something about OSHA, because OSHA now has for probably 15 years now on requirements for structural connections for the erection of structural steel. All right, connection design and the Code of Standard Practice. This Code of Standard Practice is a document that a lot of engineers are not that familiar with, but it's in the manual. Every AISC manual has had an edition of the Code of Standard Practice in it, and you should be aware of that. Engineers have gotten themselves in trouble by referencing this in their specification, but not really knowing what's in it. The Hyatt Regency, 1981, was a case in point on that. The only thing that I'm talking about here for the Code of Standard Practice is there are three options now for connection design. Option one is that the complete connection design is shown on the structural drawings. These we refer to as EOR, or Engineer of Record mandated. Option two is experienced detailer to select connections based on structural drawings or manual. These would be basically simple connections where there's no design per se, but rather just a table lookup kind of thing. And then there's three where the connections are designated to be designed by a licensed engineer working for the fabricator, either working directly for the fabricator or a third-party consultant that specializes in that kind of activity. For option one, engineer mandated, all information is needed. You, engineer of record, need to specify the bolt sizes, the spacing of the bolts, the edge distances, the bolt gauge, cross centers, pitch, weld sizes and type. Is it a fillet? Is it a PJP? You can't just show a weld symbol and not give a size. In that regard, you should know that showing the old CJP symbol no longer means CJP. Go to AWS D1.1 and look it up. It just means a weld that develops the strength of the base metal. Plate thicknesses, sizes and grade, etc. Anything else you can think of to make what you're presenting detailable. This shows a kind of typical EOR mandated connection and what the fabricator needs to actually build it. You need to know everything. There can't be anything left for anyone but the engineer of record to choose. For instance, you see an 8-inch dimension here from the lowest bolt in the beam to the highest bolt in the gusset to column web connection. If you move that, it may change the force distribution. I don't think it will particularly in this case, but it might. If this were a column flange, it definitely would. We need to know the pitch of the bolts, which seems to be kind of missing here. I see I got 4 bolts with spacings, but what's the spacing? So there's something missing on this. Nope, here it is over here. I guess 4 bolts at 3 inches on center. I've never really seen it done that way, but that's fine. That's a way to do it. The bevel's given, either the bevel or an angle. The fillet weld over here, 1/4 inch both sides. The length of the fillet is 1 foot 6. Everything is spelled out. The weld here, 3-sided, 1/4. That means top, vertical, and bottom. And since it's typical, that covers the one on the bottom. Since the angles presumably are the same, they're what, 4 by 3 by 3/8. That would be a typical engineer-mandated connection. Then for option 2, that's basically what I said, table lookup. You might need to just, the engineer might specify he wants double clips, double angle connection, so you can use this table 10.1 and similar tables. This one's for 7/8 bolts. You could pick the number of rows here, the size of the bolt, and this table gives you what it's good for, what the design strength is, and you have to make sure that that design strength is greater than the required strength, the demand. For option 3, connections by the fabricator. The fabricator can select the connection best suited for their shop. For example, maybe shear tabs to double angles, or vice versa, or welded bracing to bolted bracing. The connection engineer shall review shop and erection drawings to make sure that his requirements are met. The designer in this case doesn't just design the connections, but he's got to make sure that the fabricator has produced the connections that he's designed. This would be kind of what you might see, like the one on the left is maybe the engineer shows shear tabs, shop welded, field bolted, but the fabricator for some reason doesn't like that. He wants to use double angles, which is what you see in the right picture, that are shop welded and field bolted. Or it could go the other way. The engineer might show the one on the right, and the fabricator wants to use the one on the left. I mean, if the calculations show that these 2 connections that are shown here work for the demands given, there should be no problem with that. What this says is most any connection should be acceptable if it satisfies the project design requirements. The fabricator does not necessarily need to use the EOR's typical generic details, which is the one shown here on the left. Okay, basis of connection design. I think this is sort of the heart of the matter, and it's really going to be the basis of almost everything that I talk about in subsequent night school sessions. We'll talk about connection design tools and methods, assumptions and uncertainty, and I think the lower bound theorem is really the penultimate theorem that has to do with not only connection design, but all of the design that we do. And connection design, art and science. Connection design has been called the last bastion of rational design. That was by me. There's a lecture that I've been giving around the country over the last, 10 or 15 years with that title. And there's no question that it's hyperbole. But it has, I think, a serious point behind it. That most of connection design is based on first principles because there isn't software available to do it for you. I'll bet that probably 90% of what you engineers that are listening do use some software, for instance, to design your mainframe. GT Strudel, RISA, ETABS, STAD, or some version of STAD. I don't know if that one's around anymore. And that's great. I mean, that makes it pretty simple. I'd say if you're using those programs, you should know how to use them. I would say it would be prudent to maybe use 2 different programs to solve the same problem to make sure that you're getting the right answers. But connection design, I'm not talking about the stuff you can look up in a table, but I'm talking about that lead-in slide that I showed you that showed really complex connections. You can't find anybody's software to do that for you. So connection design is based on first principles, without the aid of complex computer models, and with little codification. The codification that exists, we've already talked about. I mean, it's sort of the limit states for all the different parts, but there's no specific codification about what particular set of internal forces you should use for these connections. This last bastion of rational design talk, really, I use that, and there was a quote from an engineer in the UK that said, any fool can design a structure, but it takes an engineer to design a connection. And his point was, on a ferry terminal collapse, that the ferry terminal building and the ramp and everything were fine. They were all done by some computer program, but the details of how that ramp was connected to the building where it was done was not done by any program, and it wasn't done right, and the thing failed, and a half a dozen people died. And he was the expert witness to explain maybe why that happened, and that was his quote. Any fool can design a structure, but it takes an engineer to design a connection. Now, again, that's hyperbole. But the point is that with connections, at least with complex connections, you can't use somebody else's software. You have to know first principles in order to do it. This is a quote that Larry Muir came up with. I don't know that the title is exactly right, but anyway, in no other important industry is the responsibility for design so far removed from the responsibility for production as it is in our industry. I mean, the engineer of record designs the building. He may design the connections on the West Coast. That's standard. Everywhere else, it seems to be that the fabricators get to do it or to hire a third party to do it. But in most industries, like say aircraft, Boeing, they design airplanes and they build them, whereas we don't. Somebody designs it, somebody else maybe fabricates the steel, and maybe a third party even erects it. Depends on how it is put together. It's been estimated that about 50% of the cost of erected steel is related to connection design. That's not exactly my estimate, but I think it's right. If you think of what it takes to actually do a complex connection, somebody has to design it. There's time involved with that. Somebody has to detail it. There's time involved with that. Somebody has to do drawings, shop drawings, to produce it, to actually make it. It has to be put together. Then it has to be shipped. So if it's not easy to ship, that's going to cost money. Then it has to be erected. And then you've got painting or galvanizing and things of that sort, and depending upon the connections, that could be easy to do or not so easy to do. So if you put all that together, I don't think the 50% is all that high. And maybe not for a Walmart or a Home Depot or that sort of thing, but for any kind of a really complex building, it's probably not too unreasonable. So, connection design. The primary tools used by the connection designer are free body diagrams, the lower bound theorem, empirical data distilled into rational design procedures, and intuition based on experience. That first item there, free body diagrams. You'd be surprised how many engineers do not know how to do a free body diagram. You might say, I don't believe that. But we hire a lot of four-year graduates from really good schools, and we give them a little test to start to see how they do. And some of them really, even to do shear and bending moment diagrams, they want to use some computer program to do that. They don't want to sit down and draw the thing. To actually do a free body diagram. The lower bound theorem is one of two theorems of limit analysis. And I think it's the most important one for the kind of stuff that we do. Most of you have probably seen the upper bound theorem. That's the yield line theory kind of thing. Is the upper bound theorem of limit analysis. So, analysis of connections. And I said before, this is sort of the heart of the matter. Really, we don't know the distribution of forces in the structures we design. You may think you do because you're using a fancy computer program, but do you really? Why am I saying this? Well, because you've made all kinds of assumptions. in the analysis procedure. You've assumed, and your computer programs have assumed that the material is isotropic, homogeneous, elastic probably, for the linear elastic analysis, plastic or perfectly plastic. All the simple connections are pinned. There's no such thing as a simple pin connection that has no moment capability whatsoever. Or maybe they're moment connections, and there's no such thing as a moment connection that keeps the angle between the two members exactly 90 degrees, or whatever the original angle was. And then many, many other things like laterally supported, torsionally restrained. You know what a torsionally simply support is? Does your computer take care of that for you? And many, many more. This is a pin connection. Does it look like a pin? Not really, but that's how it was designed. This is a truss that's supporting 35 stories of a 38-story building in Boston. All the members are 14 by 500-pound members. They all have on the order of 4,000 kips in them. The gussets that you see there are 2 inches thick. The bolts are A490, 1.25" diameter in oversized holes, slip critical class B. Is that a pin connection? Well, that's the way all of this steel was designed, as though all of these members that you see in here were the top chord of the truss diagonals, the truss verticals are loaded with axial forces, tension and compression only. That vertical bracing connections that you saw in that moment, this truss connection, that was designed by the uniform force method. I mean, it's not. The uniform force method was developed originally for bracing connections, but really, a bracing connection is just part of a vertical truss. And this is a horizontal truss. These connections were all done in exactly the same way that you would do, say, a vertical bracing connection. A vertical brace connection is a highly indeterminate system. The uniform force method gives you one of an infinite number of statically admissible internal force distributions, and the familiar equations that you've seen for the uniform force method in Part 13 of the manual are just shown here for reference. R is just the geometric parameter, and the four forces. This is the vertical force on the column. This is the vertical force on the beam. This is the vertical force between the column and the gusset. Horizontal force between the column and the gusset. Horizontal force between the gusset and the beam. These are just one of many, many possible solutions. And in a specific connection, the uniform force method would produce the force distributions that you see on this particular connection. And we're not going to go into the forces at this time. We will before this night school is over. The actual numbers would be difficult to follow, but the point of trying to make here is that there are no forces that exist anywhere outside the beam and the column other than the ones that you see. On this one you see a red arrow. I can't see it because it's behind some stuff here. And there's nothing else. That piece that you see here of the column is in equilibrium under those forces. The gusset is in equilibrium under this force. The piece of the beam that you see here is in equilibrium under this force. So, that's one thing that I wanted to point out. There's no additional moments that have been introduced in the column on this one or in the beam on this one. I already said all this. It's common practice to design a vertical bracing system as a pin truss, as you saw in that horizontal truss that I just showed you. The connection design model has remained true to the main member design assumptions. This is a basic tenet of connection design. The usual assumption on this type of a situation that you see here is that the beam, the column, and the brace see axial forces only. Maybe the column has got a moment in it. The column could be considered continuous through this joint, but normally the beam and the brace are pin connected to that column. I think that's the usual assumption. The design that you see here follows that. If, in fact, you've locked it all up, so that you have couples in all of the members, and shears, then we can do that too, but you'd have a different model than the one that's shown here. And whatever is assumed in here for the force distribution in the main frame, we should be using the same sort of analysis on the connection. On one of those earlier slides there, you saw this was a question that came up. If you look at this slide, you see that the brace force is actually along the one of the gauge lines of the bolts. The angles here were I think 8 by 6 angles. And I just wanted to point out, and some people have a problem with this, that it's always been AISC's procedure that if you're detailing a brace double angle that's bolted, the bolts are on the gauge line. And this was a 3 by 3 by a quarter, and the gauge line for that angle is 1 3/4. But if that same angle were detailed shop welded, or field welded if the case might be, the gauge line is not used, but rather the gravity axis is used, which is 7/8 in this case. These particular slides come from the AISC's Detailing Manual, 2nd edition. There should have been a reference on that slide that said that. That was, I think, 2002 was the latest edition of that. These are the bolt gauges that we use. If you had a 3-inch leg, which we did in the previous slide there, you see that the gauge for that is 3 1/4, 1 3/4, and that's what was used for detailing it. So some people think that you should be on the gravity axis for this, but really you can't. There's no way you could get a bolt in there at only 7/8 inches off the heel of the angle. So it's been standard practice since before my time that when you detail an angle, the bolts are on the gauge line. This table is in the manual. I don't know exactly what page it's on, but if you go to part 1 of the manual, it's table 7, 1-7A, and it gives you the workable gauges for angle legs so that the bolts and the washers and all of that stuff fit. Note, other gauges are permitted to suit specific requirements or to suit clearances and edge distances, but these are the standards unless you've got some other reason to pick something. But there's no way you're going to detail this thing with a 7/8 gauge. Okay, coming back to that force distribution that I showed you from the uniform force method, but how do we know this is the force distribution in the connection? And the answer is we don't. We don't really know what the force distribution is in the connection. And it probably isn't. Jim Wooten, an engineer that worked for a large fabricator in Little Rock, Arkansas, passed away a few years ago, wrote an article called Wooten's Third Law that was kind of railing against some of the things that he was seeing that engineers were requiring, hotspot stresses and things of that sort. And he said that steel was smarter than the engineers who designed it. Again, this is a little bit of hyperbole, but the point was that if a material is ductile, then if you have hotspot stresses in various places, they can redistribute, and the structure will be satisfactory. Going back one slide here, I mean, we really don't know the force distribution in here. Is that a problem? Do you think that you really know the force distribution in your structure when you say, let's say you use the most sophisticated program you can. Let's say you used, I don't know, STAAD 3 or whatever it is these days. GT Strudel's pretty up to date. Do you think that the force distribution on all your beams and columns is exactly what that program gives you? Well, it won't be because of all the assumptions that are made. Like I said, every pin connection is a simple connection, no moment, no way, etc. So let's go on. I think that what Jim Wooten was really talking about here, although he didn't say it, was the lower bound theorem of limit analysis, which says that the applied external forces in equilibrium with the internal force field are less than, or at most equal to, the applied external force that would cause failure, provided that all the limit states are satisfied, and sufficient ductility exists to allow redistribution of the forces. This was from Baker, Neal, etc. This actual statement here dates from about, 1952 or thereabouts. Using the lower bound theorem, a practical approach is really to choose a force distribution that satisfies equilibrium. We call that, in this seminar, an admissible internal force distribution. And your computer program, GT Strudel, will produce an admissible internal force distribution for your structure. Do not exceed any limit states. And take reasonable measures to ensure ductility. There are certain kinds of limit states that are not very ductile, like transversely loaded fillet welds. So maybe we make the fillet weld a little bit bigger to account for that. And you also have to consider stability, of course, which really is not considered directly in the lower bound theorem because it considers ductile limit states. And generally, buckling is not particularly ductile. So you need to make sure that those limit states are not an issue. But what does this mean? The designer has the freedom to choose any convenient force distribution as long as equilibrium is satisfied, no limit states are exceeded, and loads can redistribute without fracture, and they can redistribute without stability problems. Why? Force is attracted to stiffness. When a member yields, it becomes less stiff, sheds loads to other elements. If there is somewhere for the load to go, it will go there. Steel is inherently ductile. There's a series of slides here that kind of show this. This is a plot that shows the stress-strain curve for a linear elastic sort of strain-hardening material, and then what happens to Young's modulus, to the modulus of elasticity. The blue is Young's modulus, and the black, the blue is Young's modulus, and the black is the stress-strain law. And as you start increasing the load, everything's linear and elastic to start with, but you reach a point, the elastic limit. When you go beyond that, the stiffness really degrades, and so does the strength. And as the material yields, the effective E, and therefore the stiffness decreases, and the load redistributes. Now, we're assuming that there's some place for it to redistribute too. If you have a structure that's non-redundant, well, you're going to end up with a failure because there's no place for it to go. But most structures are redundant, and so therefore, this whole idea of ductility and the lower bound theorem works. Connections, art and science, the art of load path, an intuitive knowledge of how a system will transmit loads. And the science of equilibrium and limit states, an understanding of structural mechanics. And the art involves finding the load path that maximizes the external load. That's really what we're after here. We want to come up with the most efficient design that we can. We don't want to come up with a design that's dumb, that takes more material than we need to use. We don't want to use material that's expensive. We want to use material effectively. There's a corollary to the lower bound theorem that states the admissible internal force field that maximizes the capacity of the connection of your structure is closest to the collapse solution. Admissible is used here just as another way of saying a system of forces that satisfies equilibrium. Isn't it really convenient that this is the case? I mean, if this were not the case, if you could pick something that makes the building, no matter what we pick, as long as we satisfy equilibrium and the limit states, we're going to have a satisfactory connection. No matter what we pick, a satisfactory structure. At least that's what the lower bound theorem is saying. Not just for connections, but for buildings, for the whole thing. If you think that your computer program is going to give you the right answer for everything, it won't, because of all the assumptions that are made. If you actually built your structure exactly like your program says it's modeled, then I agree, you would satisfy everything, and you would get exactly the solution. But before we get into that, let's look at an example of this. This kind of shows the corollary, that no matter what you pick, you'll come up with a conservative solution, and when you pick the right solution, you get the peak. Suppose we have a system of 3 identical tension members supporting a load, shown here. This is indeterminate to the first degree, although intuitively we know each bar supports an equal load. However, if we assume the center bar supports a percentage of the load X, and the results are plotted, we come up with a pretty simple demonstration, I think, of the corollary to the lower bound theorem. For instance, the first entry here is I'm assuming that the middle bar is cut. It's carrying no load. The capacity of this structure then is 66 2/3 units, whatever they are. If I take 10%, 13%, it's going up, 73 kips, 76 kips. If I take 25% on the middle one, I'll get about 89 kips. If I take 33% on the middle one, I get 100 kips, which happens to be the true solution. Suppose I go to 50%. I'm going to put half the load on the middle one. But now I'm only back down to 66 2/3. And I can go down filling up the table with various values until I get to the last one, which is 1, which means that the middle member carries everything and the other two are cut. And you get a plot. If you plot this data here, you'll get a curve that looks like what you see here. So what are we doing here? The lower bound solution, the 3-bar structure, here's my equilibrium. All we're satisfying is equilibrium in the limit state. This is the system. I got X times the load in the middle member, and I got some other load in the other two, some force F. So equilibrium says that 2F plus X times P minus P equals 0. And the limit states are that each bar cannot exceed 33 1/3 kips, pounds, whatever. And XP, likewise, the middle one, can't exceed 33 1/3, and the total maximum load is 100 kips, let's say. So let's look at how to do this then. Let's take an example. Let's assume that the middle bar carries 50% of the load. If that's the case, the other two carry the other 50%. So I have 25% in each of them. So just setting the 0.5 P to the limit state, 33 1/3, I calculate P is 66.7, less than 100, okay. Taking the other one, the 0.25 P, setting it equal to, or less than, 33 1/3, I get P equals 133, which is greater than 100, which is NG. The solution is 66 2/3, which is exactly what we got when we picked 50% right here. Every one of these solutions that you see in here satisfies equilibrium in the limit. Every one is a satisfactory solution. But there's one that's better than any other, and that's the one that's 100 kips, which is the actual true solution in this case. More information on ductility and behavior of steel. Basic concepts of ductile detailing by Mike Engelhardt. It was in the 2009 NASCC series, Top Hits from Top Profs. I think that one is available from AISC. But before we go on to that, when you look at this system here, you have to remember what you're doing with the lower bound theorem. The lower bound theorem, if I go back, and I don't want to go back that far, but all I'm doing is I'm satisfying equilibrium and I'm satisfying the limit states. There's no other requirements for the lower bound theorem. There are 3 basic principles of structural mechanics that you have to satisfy in any problem to get, say, the true solution, if you like. Everything must satisfy equilibrium. You've got to satisfy the limit state. But there's another requirement that you also have to satisfy, and that is compatibility, which basically says that the structure, if it fits together before you deform it, it has to fit together after you deform it. Now, that requirement is not satisfied by any one of these solutions here except for one. This one right here. Compatibility is satisfied for that one. We've satisfied equilibrium, limit states, and compatibility when X is 1/3. But for all of the others, we're satisfying equilibrium and the limit states, but we are not satisfying compatibility. So really, if you think about this one, the middle one carries nothing. What we're really doing is imagining that it's cut. And this last one here, where the middle one carries everything, we're imagining that the other two are cut. So they're not fitting together anymore. So we are not satisfying compatibility. Now, when you run your computer program, let's say GT Strudel, and you get the solution to your structure, and you hit design it, and you come up with all the members and everything else, the original model that you've got satisfies all three principles. That's where it comes from. So you get sort of, quote unquote, the exact solution or the true solution. But the building is not built like your model says it is. Basically what you've got is a wire diagram with wires that have no cross-sectional dimensions, but they do have embedded properties like area, moments of inertia, radii of gyration, section moduli, shear areas. All of these things are related to wires. If you actually built the structure like your wire diagram shows it is, you would satisfy all three principles of structural mechanics, but you don't build it that way. There's no way you could actually make that work. So what I said before was, if you think that all of your structure is really the loads in your structure are exactly what you think they are from any fancy computer program you have, I'm saying no way, because the structure is not built like the model assumed it was. In addition to that, I mean, you've got the things like pin connections not really being pinned, and moment connections not really being totally rigid, and et cetera, et cetera, et cetera. All of those things tend to put error into your solution, and you come up with, I think, a satisfactory solution because of the lower bound theorem, but you're not going to get the force distribution that you think you have. I kind of learned this the hard way when I was looking at a structure that was designed about 1950 or so, before the advent of computers. It was a mill building, actually a boiler building, and it was designed by what's called the tower method. Now, some of you older engineers out there probably have heard of the cantilever method and the portal method. These are designed for lateral force distributions before the advent of computers. And there's another one called the tower method that was used for boiler buildings, where basically the boiler structure was a tower that supports the boiler, and then you had all the peripheral stuff, the lateral bracing for wind or seismic, and all of the other equipment that is supported on the structure to facilitate the production of steam in the boiler. And I took that building and had something like 10,000 nodes, and we ran GT Strudel, or a version of it at that time, and another program that was available. I can't remember the name of it, and I got the same answers for both. But all I had on this building was the footing loads, the column loads at the base of the building. And the loads that I got now, what these programs gave me, which they agreed with each other, but they did not agree with what was actually used in the design. And in some cases, we had like 400 kips in a column in the original design, and we now had 50 or 60. And likewise, we had some columns that had maybe 100 kips in them and now had 300 kips. Yet there was no distress in this structure, and I think the reason is because of redistribution of load. Even for buckling, I mean, if something can pick up the load in a column so that it doesn't have to deform anymore, it will sustain the load at which it buckles at, and the load can be distributed to other members. Anyway, this is reality. This is what happened. I can't explain it any other way. If I had a single column there, and the load was 400 kips when it was designed for 100, the building would have collapsed. But this thing was standing for 50 or 60 years, and there was no evidence whatsoever of any distress whatsoever. Anyway, let's look further here. Comparison of bracing, design models, and load paths. The next several slides will demonstrate the savings that can be obtained through a careful use of the topics discussed in this presentation, and it will be discussed in the subsequent webinars as well. And a special emphasis is placed on load paths, but all other considerations also have been accounted for in these optimal designs. And I'm subtitling this as load paths have consequences. Or in other words, let's look at the bottom line. There is a method called the KISS method, kind of sarcastically called that. It's the keep it simple, stupid method. This method has been around forever. What you see here in this particular slide is an admissible internal force field. Satisfies all the requirements. And there are no couples in the column or the beam outside the connection, but you do have big couples between the gusset and the column and the gusset and the beam. I don't know what other names this goes by, but I'd say the KISS method, keep it simple, don't make anything more difficult than it needs to be, is as good as any. The KISS method was used with and without couples, the moments, M sub B and M sub C, but mostly without. It was used with the brace vertical component on the column connection and the brace horizontal component on the beam connection. It was used without regard for where the work point was. Was it at the gravity axes, or was it at the corner of the gusset, or some other place? These are inadmissible force fields. An inadmissible force field does not satisfy what William McGuire of Cornell said in his book, Steel Structures, Prentice Hall, 1968, page 933, which I think is a really neat quote. This is in another context, but it really applies here as well, that an inadmissible force field does not satisfy the niceties of structural mechanics. A lot of this material that was done years and years ago was done before we really understood things like eccentricities and what have you. I mean, for instance, bolted connections really derive from riveted connections, and riveted connections derive from probably turn of the last century, 1910, 1920, maybe even 1890, a long time ago. And they just tried some things and they worked. On the other hand, welded connections really didn't develop much until after World War II, maybe 60, 70 years ago. And by this time, we understood the niceties of structural mechanics. And so if you go into books on connection design, you find lots of times eccentricities, small eccentricities, 3 inches and what have you on bolts are ignored, but the same eccentricities are not ignored on a welded connection. Why is that? Well, this was the context in which Bill McGuire said this: the niceties of structural mechanics are satisfied now for welds, but bolts really were done based on rivets, and we didn't know enough about things back 100 and some years ago to really get into it, and there's never been any problems with it, so they're still done that way for the most part. In particular, if you don't have an admissible internal force field, the lower bound theorem is not valid. So you're up the creek without a paddle, so to speak. Although I really think down the creek without a paddle is probably worse, because at least up the creek you got the current to take you back down. So you really don't know. You don't know whether it's okay or not. Is it okay? I don't know. But if I satisfy equilibrium, I know that I have the lower bound at my back as long as I satisfy all the limit states. Over the years, I mean, I've done lots of different ways to do this, and I always, no matter what I did, if I missed something, somebody would catch it, and they would say, "Well, you didn't satisfy equilibrium here. You've got an eccentricity there." The KISS method is a perfectly acceptable way, and it satisfies all the requirements. So does the uniform force method. So does the parallel force method. So does the truss analogy method, which we won't discuss here very much, but it's certainly a viable method. But is it economic? The KISS method versus the uniform force method. Is there an economic reason to use KISS? If you're going to do one of these, I don't think it makes a heck of a lot of difference. But if you're going to do 1,000 of these connections, it makes a big difference. It is simpler. There's no question about it, even with the couples. And as I said, the couples were generally not used. I've talked to people from American Bridge and from Bethlehem Fabrication, and they basically did this. They did not consider the couples. They didn't worry about the work point location. They put the vertical component on the vertical edge and the horizontal component on the horizontal edge, and they let it go at that. I mean, there's plenty of buildings standing like that right now. I think they're probably okay, but they don't satisfy the niceties of structural mechanics, and you can't get away with it today. If you were to try that today, I guarantee you somebody will catch you, maybe a building inspector or a peer reviewer or whatever, and you're gonna have to do it again. Back in those days that we were talking about, I don't think anybody really questioned American Bridge. If they said this was the way to do it, this is the way to do it. Okay, let's compare designs. This shows you a design by the uniform force method on the right and KISS method on the left. Exactly the same loads. The design by the uniform force method is contained in the AISC solutions that you can download. It's in the 13th edition download. It's also in the 14th edition. The one on the left is not, but you know what the force distribution is. You can do it yourself, see what you get. Anyway, what's the difference in cost? About $182. I mean, I would like that to be a lot bigger, but it was about $840 for KISS and about $660 for uniform force, about $182 per connection. If I had a 40-story building with 32 of these per floor, 32 per floor, 40 floors, lots and lots of them, you're talking about $250,000 between these two. That's just in material. Fabrication, just fabrication, erection, shipping and erection it's not even included in that. That's going to add to it. Well, the parallel force method, which is a perfectly good method. However, it's not universal. It doesn't work really good for column webs. Oh, but let's look at it. This is the admissible force field for the parallel force method, which is a method we'll discuss in some detail in the next session. The problem with it is I get 79 kips in this particular example, normal to a web. And that really is hard to carry on a web. And I end up with a whole bunch of stiffeners between the gusset and the column here, and another whole bunch of stiffeners down here, and I come up with a double plate because I got such a heavy concentration of load in this region down here in the beam. If I do the same thing with the uniform force method, you can see right away that it's smart enough and set up really so that since I'm going to a web, I don't have anything perpendicular to the web. And if I do that design, I end up with something that looks like this. This is designed by the uniform force method. I think you can. I don't have any costs for this, but you can see a big difference. Load paths have consequences. The uniform force method with the uniform force admissible design, force field gives me about 320 kips capacity. If I do the same, take the same design, the uniform force design, but I stick it with the KISS internal force distribution, I'll get a capacity of 236. And if I use the parallel force method, internal force field with the UFM design, I'll come up with a capacity of about 86 kips. So you can see the same thing is happening here as in the 3-bar structure. I think the uniform force method is closest to the true solution, closest to satisfying all 3 principles of engineering mechanics. And the other 2, KISS is actually better in this case than the parallel force method. But if I went to a column flange, I think you'd find the parallel force method is better than the KISS method. Well, load paths have consequences. This is a job that was done in Georgia some 5 or 6 years ago. We saved $2 million on this job. That's the engineer of records estimate. Their original budget price on this was for using the KISS method. We used the uniform force method. We used conventional and extended tabs instead of the more traditional double clips and jumbo columns. We used, as I said, the uniform force method in novel ways, as we'll see in the next presentation. We used X bolts. That's something that you should consider. X bolts generally will have the threads excluded when you're when the thickness of the plates is like 3/4 of an inch or better. I don't know exactly what the numbers are here, but there was a seminar done, Practical Connections, and you may have a copy of it kicking around your office. It's got a table in there that shows you exactly what thickness you need close to the nut to exclude threads. You shouldn't just say, I'm not going to use X type because there's more inspection. Not necessarily. It depends. 3/8 plates, absolutely. You better use N type. Anyway, this was the kind of the novel connection that we used on this. This is what I'm calling the optimal load path. This would be the more conventional one with 2 different shear tabs. The difference between these two is that we're kind of treating this as though it's the connection. This connection is to a column flange. These bolts, the first column of bolts here, are all at E sub C. You'll see that in the next slide or subsequent slide. You won't see it yet. But anyway, the weld size is on the optimal with 5/16 as opposed to 5/8. We had a 1/2 inch plate as opposed to a 1 inch plate. We had smaller bolts. We used 3/4 bolts with the optimal. This is the one that was actually used on this job. This is the one that we might have used without this optimal approach. What are we doing? Basically, this is what we're doing here. E sub C, which we'll get into in the next section, is the eccentricity. It's half the depth of the column. What we're really saying is that even though this is a web connection, the uniform force method can be made to work with an E sub C equal to the distance out to the first column of bolts, as though we had a column flange connection. And the force distribution for that is given here. You have a handout for this. I believe you can check these numbers to see that it's correct. And that's really what I mean by innovative stuff. You need to look at what you're doing and see if you can't do it better. And I think that this particular model here, with the E sub C at 10¼ inches rather than 0, which is what it really is, if you go to the face of the web or the center of the web, gives you one heck of a difference in the cost of this connection. And the final slides here just kind of show that. With 80% savings in drilling time. We had to not drill as many columns. We had 50% savings in weld consumables. And I think I'm kind of running out of time. So I'm kind of just not going into great detail on this. And 60% savings in welding labor. These are all big deals. And the bottom line on this job was, and what you see here for the optimal case, this one right here, the optimal load path is what was used on this job. According to the engineer, this is the owner's engineer, not us, that their budget price was $2 million above what it actually cost to build it. 30% savings in material because we got thinner plates. Okay, summary. I mean, we will get into this in the next night school class. I mean, I'm just sort of hitting the highlights here as kind of teasers, but in this presentation, we've reviewed the basic principles of structural mechanics and bracing design, which really apply to everything, not just connections. We have shown the design achieved depends upon the load path. Your computer programs assume a load path. We have shown the importance of the lower bound theorem. The lower bound theorem converges to the true solution from the bottom. The upper bound theorem, which you're more familiar with, the yield line analysis, for example, converges from the top. And next week, we will look at the uniform force method in detail. We'll derive all the equations, and we'll do a few examples to show how to use it. And with that, I guess I have to say I thank you for your attention.
Okay, thank you very much, Bill. We do have time for a few questions here, so if you have any questions, feel free to type those in. Our first question, Bill, I'm going to take us back to slide 61. I'll go ahead and do that. This is in regards to the angle gauges. So you mentioned that if you detail the bolts to be on the workable gauge, is it then standard practice to account for the moment to the center of gravity in the angle of the connection?
The question is, since we're not using the gravity axis on this when we do this to the bolt gauge, are we accounting for a moment? The answer is no. We have not. Generally, we do not account for the small couple that would be generated in this case. I don't know that it's exactly spelled out in the specification, but I do know that if you have a welded situation, for example, where you've got a heel and a toe, you do not need to balance the wells to get the gravity axis of the wells lined up with the gravity axis of the member. And so it's not done here either. In this particular case, you'd have a small eccentricity, and it's ignored in the calculations.
We have a couple questions regarding the use of the uniform force method versus the KISS method. And I guess the question is, how do you see the current industry? Are they still using the KISS method, or is everyone typically using the UFM?
Okay, the question is, what do I see in industry? Are people still using the KISS method, or are they using the UFM? I would say very few people now are using the KISS method. I mean, normally what we see on engineers' drawings is either they explicitly mention the uniform force method, or they don't really say anything at all. And for us anyway, for me, for surveys, we would be using the UFM in that case. I haven't seen a recent job where the KISS method or something similar to it was actually spelled out. So I guess to reiterate, what I'm seeing in the industry is the uniform force method, or the engineer leaves it up to the connection designer to pick a method that he likes. But I don't think I've seen in the last 10 or 15 years anybody show a distribution on their drawings, whether they called it the KISS method or didn't have a name for it, that actually showed the distribution that I showed you here for the KISS method.
Okay, we have a question about analyzing base plate connections. If you have a base plate that you've analyzed as pinned, should you still consider some moment for that design?
Okay, if I have a base plate that I consider as pinned, should I still consider some moment in that design? I don't know the answer to that question. I know that for non-seismic, we have generally not done that. I do know that in seismic, this is a hot button item that some moment needs to be considered to make sure that you have ductility. But I think that particular issue is still up in the air. There are people working on exactly how this should be done. So I don't have a really definitive answer for that. For non-seismic, I have never considered a moment if it was considered to be a pin base. On seismic, I think the jury's out on that one at this point. Next.
Okay, I'm going to go back to slide 24. This is in regards to welding. When you were going through the different sections and where you'd find limit states, you mentioned that the check for weld yielding went away, yes, and only rupture. Can you explain further on that?
I guess the question is, can I explain further why the yield limit state on rupture on the base metal adjacent to welds has gone away? I think the feeling is that the weld limit state itself is a rupture limit state, and the base metal is right next to the weld, and so therefore really it doesn't make any sense to have a rupture limit state on the weld and a yield limit state on the plate right next to it. That's the only explanation I can give. I really wasn't involved in when this was done, but I think it's a step in the right direction. And you can see that if you look at section J2.4 in the 13th edition specification, and look at exactly the same in the 14th edition manual, you'll see what I'm saying. The 13th said that you had to check yield and rupture. The 14th says just rupture. But there really isn't a lot of difference between them, because for yield, especially shear yielding, the resistance factor, say, is 1, and you're working against the yield strength, say 50. And for rupture, the resistance factor is 0.75, and you're working against the ultimate tensile strength, which is 65. And if you calculate the numbers, it's not really a lot of difference. I think people were thinking maybe it's a little bit redundant to do too, but I do think that logically it makes more sense to have a rupture limit state for the base metal adjacent to a rupture limit state on the weld. And I think that that's the way it's going. I think if you look at the Seismic Manual now, there's some examples that are done with both yield and rupture, and some examples that are done just with rupture. And this was in the 13th, and it's not. No, it's to the 14th. So some of them were still using the yield limit state, which we really don't have to do anymore, because people are just so used to checking yield and rupture that they just check both. And I'm in that category. Some of the ones that I did for that manual, I just checked yield and rupture, or I checked the one that had the less capacity and said, well, that's good enough. But I think it's logical to repeat myself for the third time that since you have a rupture limit state on the weld, a rupture limit state on the base metal right next to it makes more sense than to have a different kind of limit state on the base metal.
Okay, here's another question for you. Can you discuss a little bit the advantages or disadvantages of using tabs at bracing connections versus, say, double angle clip connections?
Okay, to repeat the question, can I explain why using tabs is advantageous relative to, say, double clips? I would say that the advantage of the tabs is primarily in erection, because it's extremely easy to erect a beam with a gusset plate if you can bring it in laterally and pin it. Whereas if you have double clips, you've got to basically kind of jam it between the column flanges if you're talking about a flange connection, or you've got to drop the thing down the column web to get it in place. And if there's a stiffener or something in there for a moment connection in the other direction or at a different level, that might be a problem. The tabs make the erection very simple. One of the disadvantages of the tabs is that you've got bolts in single shear, so you might need more bolts. But we have found that the cost in the shop is more than offset by the savings in the field in the erection of this. One of the early slides that I had here in the beginning, if I can go back to that, the one with the big one right in the beginning, I've forgotten the number of it. It's like slide 3 or 4. I got you. Yeah, there we go. Look at that one. I mean, that's got shear tabs to the web. We got 3 columns of bolts. I mean, it's got lots of bolts. But the erection on that was really slick. And going into the column web, we've got on that one, I think double clips. It's hard to see in the picture, but I'm pretty sure it's double clips. Double clips would, I think, be the second choice. End plates is probably the third choice in terms of economy. The double clips have the advantage that the beam could be cut a little bit short, and you can take up the slack in the proud dimension on the clips or the setback dimension on the clips, whereas if you've got an end plate, the thing's got to be cut just about perfectly to start with, or you're kind of dead in the water on it. Shear tabs are really a very inexpensive connection for the field. They do encompass extra cost sometimes in the shop because of the number of bolts that you have to use. Okay, next.
Okay, we're getting a handful of questions regarding the uniform force method, and just to reiterate, session 2 will go in depth into this topic, but I think this is a good question to ask Dr. Thornton here. Is the uniform force method applicable in horizontal brace design, and if not, why not?
Is the uniform force method applicable in horizontal brace design? And if not, why not? Well, I think that generally for horizontal braces, we're talking about a wraparound gusset, and the distribution of forces is just a lot simpler than that kind of connection. And usually, you're not really worried about the connection of one beam to another beam, but there's no reason why it couldn't be used. If you had, say, one beam running through a joint and the other beam stopping, then you could say that what I'm calling the other beam is the beam, and the continuous beam is the column. And you could use the uniform force method there. There's absolutely no reason why it couldn't be used. You could use the KISS method, too, if you want to. But I don't see any big advantage to using it in 9 out of 10 of those, because we basically use a wraparound gusset. You end up with a cutout in the corner of the gusset to get around usually to get around a column, because usually these connections are going to be horizontal beams framing to column flanges and column webs. But there isn't any reason why you couldn't use it. I think it's simpler probably to just go back well, we'll have to talk about that in one of these sessions. Maybe that'll be in session 8. We'll maybe do some wraparound gussets. But I've never really used the uniform force method for a horizontal brace, but there's no reason why you couldn't.
So I guess to piggyback on that question, another question came up: is there ever not a situation where the KISS method is more economically feasible than the UFM?
Is the KISS method ever economically more feasible than the UFM? Well, for instance, if you had a connection to a column web and you had a beam that was laid on its side so that you're connecting to a web instead of a flange, you wouldn't have any couples with the KISS method. I would say you would probably come up with pretty much the same design for both of them. I don't know that I've ever come up with a case where the KISS method was more economical, but I think that there might be some cases where it's really not that bad. And really, as I said, I think in my presentation, if you only got 1 or 2 of these and you want to get a solution out pretty darn quick without messing around, and you don't have any software or anything to do this, the KISS method is not going to give you that bad a connection. It's really kind of bad for the bolted part of the connection, because when you put a couple on a say double clips or something like that, the bolts at the top and the bottom really see a lot more load than they would if they were uniformly loaded, which is what you'd get from the UFM. So you end up with maybe a deeper connection. You end up with heavier angles, say if we're talking about double clips. I think in general, the KISS method is not really the way to go, except maybe in the instance I just said, or if you only got a couple of them. I mean, who really cares if there's only one on the whole job? You can just be done with it. Okay, well, I think that we're done. I thank you for your attention. I don't know that I've answered all the questions, but I guess we will try to do that in the future, and hope to see you next week. Okay, thank you very much, Bill. And thank you all for joining us. I do want to go over some quick announcements one more time before we wrap up tonight. Package. For the 8-session package, you will only be receiving a single certificate for one person, that being the registrant. And those will be issued at the conclusion of the entire course. So hold tight till the end for that certificate.
Additionally, with that 8-session registration, you'll be getting access to the quiz as well as the recording. How that system works is you'll get an online form that you can take that quiz, and quiz as well as your attendance records are posted every Tuesday morning at aisc.org/nightschool. If you go there and then click on current course details, you can keep a lookup of what your quiz scores have been. So why would you want to take those quizzes? Well, we are offering the EEU, which recognizes those that partake in taking and passing the quizzes as well as the final exam. You must take all the quizzes in the final if you want to receive that EEU. Additionally, if you do not catch the live session, that'd be the Monday night session, and you only watch the recording, you have to take and pass that quiz in order to receive your CEUs. But this third one, I want to emphasize, we certainly encourage everyone to take those quizzes that are signed up for that 8-session package. It really serves as good reinforcement for what we're teaching in this 8-session course. And I mentioned this already, but again, if you do attend the live session, to be clear, you do not have to take the quizzes to get your PDH credits. One more item regarding the 8-session registration is you do have access to the recording. In that information will be included in the email along with how to access the quiz. That concludes this evening's session. I want to thank you all for joining us. Thanks once again to Dr. Thornton for tonight's presentation, and we'll see you next Monday. When we conclude tonight, there will be a brief survey that pops up. We do appreciate you taking the time to give us some feedback on this evening's session. Good night, everybody, and we'll see you next week.